So now we can look at a simple example. And what I normally like to do when we're doing these courses is to run these sorts of examples interactively and have you actually build the model and type the data files and understand it, what's happening at every point. What we're gonna do instead is, I would like you to follow along, but we're not gonna build everything. You can just read and look at data files that are already been created in that folder. So if we switch to FLAC2D, and if hopefully everybody can get FLAC2D launched, there is in the day 2 folder, then you go to groundwater, then you go to exercise, and then you go to solution. We're just going to load the fluid project, okay? Oh, we're looking at, just again, day 2, groundwater, exercise, solution, fluid.prj. And open it up. Wow. I don't know why the text in the file dialog is so tiny here. Weird things happen when I change resolution. Hopefully. And what you hopefully will get is something that looks kind of like this, with a bunch of data files and a bunch of save states that are already there for you to use. Okay. Also were a bunch of plots, but there was some hiccup between versions and the plots disappeared. I'll have to make those again. So let's look at, so the first thing we would do is generate a model that looks like this. This is a simple slope, okay? And we do that in the sketch tool, and we create zones with it. And it's important to note we label these two groups surface so that we can do things to them later. And that's all covered in geometry.dat, okay? Which is a data file that recreates all of that and generates the geometry save state. So if I were to run this now, you can see by going to the sketch tool, hello, variable has happened to my font sizes. Sorry about that. If you go to a sketch set, I don't want a new sketch set. I want, yeah, this one. Just click on that. You can see that that's what we created. And that generates this geometry.save state, which if we go to model pane, we can see. Now, what we're going to do is we're going to start with that. Oh, by the way, I want you to note that unlike when you look at this in the model pane, I actually included this region in the slope, right? I don't know to what extent we talked about nonlinear effects. I'm going to do, even though I'm pressed for time, because I think it's important and I'm not sure what was covered yesterday, I'm going to briefly, this is a great way to show the importance of initial equilibrium and nonlinear behavior. So if we look at this model slope.dry, this is just the dry equilibrium before we start adding the effects of water. So we restore the geometry, we set large strain off, we assign a more Coulomb constitutive model with zone C model assigned. Now this is just assigning properties, and in this case, I did it using the tool in the model pane, which you might not have seen, that lets you assign constitutive models and properties. That's why the commands look funny, but really you can just do this. Thing, okay? And we've got more Coulomb material properties, including cohesion and friction. And we assign roller boundaries on the left and right, and fixed velocities on the bottom. Initial gravity, initial stresses due to gravity. And then we take a history of convergence, like you always do, and then we solve, and that's our initial state. Now note that that initial state in this includes, this is the whole thing. This part hasn't been excavated yet. It's just a simple square, okay? It should be super close to equilibrium automatically when you do the zone initialized stresses. The only reason it isn't perfectly in equilibrium is because you've got distorted zone. Excavate that region above the slope, right? So we use zone relax excavate to excavate this, and then we come to equilibrium and we save that as our dry state. Okay. The reason is we're trying to follow the path of whatever created the slope. The slope existed with these materials, and then somebody excavated the slope, and that's how we get our initial conditions. Now, the reason why I'm making that clear is because there is any number of ways to kill a cat, right? And people use different methods of coming to that initial equilibrium. And one way is that you can just delete the zones. You can say, get rid of those zones and don't relax them. So it just happens all at once. In that case, if you're on a slope and you're very close to failure, you can get quasi-inertial effects that change the extent of damage around that excavation. Okay, that's why the zone relax excavate command exists, to slow that down, to try and maintain. Or another third case is you can not initialize the stress field. We initialize the stress field to gravity first, and then we came to equilibrium and we excavated. A lot of people will just, say, here we are. Now I can solve, and it will adjust to gravity over the course of the solve. And that will give you a different initial state. You start up with stresses of 0, and you build up stresses due to gravity over the course of the solve. And then there's a fourth case where we do that, but we solve elastic. Solve elastic means, okay, we know that everything's going to go crazy when we do this solve due to gravity. We're going to get a lot of transient failure. So let's fix that by solve elastic means you solve in 2 steps. First, you do an elastic to equilibrium, and then you turn failure back on and allow it to fail. So this does a solve elastic. It'll adjust to gravity elastically and then fail. Now, the point I'm trying to make quickly, because I don't have a lot of time, is that this is 4 different, FLAC2D is made to model nonlinear material behavior. That's why, that's its modus operandi. That's like its life. Nonlinear means it's all about the path. This is 4 different paths. So you're going to get 4 different stress states. And you can actually run this, and it'll generate all 4 of these, slope dry. Now, if I make a plot, oops, that's not what I meant to do. Clicked on the wrong. Let's make a plot. Here's color by state. So we can see this gives us the extent of failure in the model. And we can go through, here's the one I did, the initial one, where we've got failure here and here. There's a little bit of failure in shear at the toe, and there's a little bit of failure, but that's all in the past and it's stable now. All 4 of these are stable. The second one has a difference, has more failure because we didn't zone relax. So we got more failure around the surface. This one has failure everywhere. The whole thing failed on its way down. And then we used elastic, and we got yet another range of failure. In this case, this part, but we got more failure here than we would have otherwise. Those are 4 different failure paths, right? And because of that, if we contour things like, oh my gosh, this did happen to me last time. For instance, this is minimum principal stress. You'll see that there's little adjustments made to the minimum principal stresses in all 4 cases because they each followed a different failure, nonlinear failure path to get to an equilibrium. They're all in equilibrium. They're all in slightly different equilibrium. Okay, so remember that. Path is everything in FLAC3D. So pay attention to your path. right. I will, that's a little aside, just because I got excited when I started looking at this example. I went, this is the perfect way to show this. Okay. Now we're going to go back to the zone fluid. Now, if I can see anything in this, this is a new laptop and a new system. Let's look at zone WT. This is zone water table. So now we're going to start with that zone dry. It's slope dry. One of the four initial states, the one I like best, the one that used initialize stress and zone relax excavate. Okay. Initialize the displacement field back to 0 because we want to know what the displacements are after we add the water table. We want to know what the water table effect the water table has on our system. And we can not only initialize our displacement, but we can also initialize the state. So all those state flags indicating failure, we can clear those to 0. So now we can see what additional failure happened after we add the water table. So this is resetting both our displacement field and our state. Note, to those of you with finite element background, changing the displacement field does not change equilibrium in any way. That's just a tracking value. It's not an important physics value, all right? Because everything happens incrementally in FLAC2D. We just are updating displacements as we go from strain increment to stress increment. It doesn't actually affect anything. So we can change it at any time. It doesn't make any difference. Okay? It's a little mechanical equilibrium of the system. Here we import a water table, DXF, which is a 2D, that 2D line you saw on the plot earlier. We set the water density to, in this case, 1 for the sake of this example. And then we set the pore pressures based on that water table. So we've got gravity, we've got fluid density, we've got a water table surface, and now we've got a pore pressure field as of the zone water set command. What we don't have yet is wet densities below that water table. So if we just run this much, then I can do that with, I don't know if you've seen it, this run selection option. We switch back to this plot. But below here. Hard. Okay. Here. At the zone water set command, we generated a nice set of pore pressures. Right. There's nothing negative, right, above the water table. So it's just goes from 0 to wherever based on, and it's strictly due to gravity. Now we're gonna use these commands to set densities below that line to be a little higher, because we want to account for the presence of fluid in them. Again, remember, we have to do that manually. So we're going to use this, and you might not have seen it, we're going to use this range called the geometry space, which is one of the range elements supported by FLAC2D that allows you to set things in relation to geometric sets. And what this geometry space does is it just, you've got a surface, it sits at the centroid of the zone in question, or the grid point location if you're filtering grid points, and it sends a ray out in a direction, which always defaults to up. Counts how many times it intersects that geometry set you specified. And what count odd says is that if it's an odd, if that count is odd, it's considered inside the range element. If it's even, it's considered outside. So what that does for our purposes is our hit count is either going to be 1 or 0. 1 if we're below it, and 0 if we're above it. So if we're below it, we're inside the range, and if we're above it, we're out. So that's basically a way to select all the zone centroids below that surface using that geometry space range element. And we set the group name wet to those zones to make it easy to refer to them later. And that's what we do, is we immediately use that group, those group assignments to set the density to be higher. Our porosity is 0.3, our water density is 1. So we increase the density from, this is what the original density was. We increase it by 0.3 times 1 in those zones. And we haven't configured fluid, so we have to do that ourselves. Well, these kind of commands make it easy. Now we've got all the adjustments we want to make to the existence of water for this model. We've increased the density of the zones below the water table, and we've set the pore pressures below the water table. So now we can solve to see what effect that has. And we can just run it. And see. Now, I'm going to make different plots because to find stuff in those menus is going to drive me bananas. Why that was okay. Here is what you can see, by the way, when I look at the zone, I assign those groups wet. So all of this stuff, this is the zones whose density were changed when you look at the zone group plot. If I can, well, the color's a little bit unfortunate, but all this red hasn't failed. So we got a little bit of tension in the upper right. That's a boundary condition effect of the slope. We got some shear failure at the bottom here because we were already close to this failure. So when we changed effective stress, it failed a little more. Note, it's still stabilized, but it did fail in shear for a while before it stabilized. Stuff in the upper right, that's just because the boundary conditions are too close, but it's a small model. So. We can also see, remember we make another one. Remember we initialized our displacements. So those are the displacements that were created due to the addition of the water table. This is what happened after we added the water table. And you can see this is very clear. It's trying to fail. It started along a classic slope slip line, but then it stopped, stabilized, okay? Are there any questions? On the right side? Yeah, remember we saw there's a whole lot of tensile failure up here. So that, and that's again because the boundary conditions are too close. And you see this a lot in slope models, actually, even when the boundary conditions is a lot, because what, you know, the direction everything goes like this. This tries to fail, and everything here has to come this way. So if you've got any kind of a fixed boundary condition here, you're going to see some artificial tension. Don't panic, it's just a boundary condition effect. Well, you can just ignore it if it doesn't affect you, because generally what you're interested in is like surface subsidence or whether the slope fails or not, right? So a little bit of artificial mucking around over here isn't really going to affect your solution anyway. But if you could increase the tension there to make it stop happening, you could use a pressure boundary rather than a roller boundary. There are things you can do, but for the most part, people say, "Oh yeah, you've got failure in the upper right corner on a slope," and go on with life.